I told no, there are two derivations on Gauss's theorem to work out the field due to a uniformly charged symmetric body, only symmetric body. The wire is a symmetric body, the sphere is a symmetric body, the plate is a symmetric body. Which is the symmetric body? On a line, if the symmetric body is divided into two parts, two halves, then the two parts are equal, exactly identical. So, for a uniformly charged, charge should be uniform. Everywhere the charge density should be same. Uniform means everywhere charge density should be same. Charge should not be concentrated heavily on one part and rarely on another part, not like that. Everywhere the charge density, number of charges per unit area should be same. Okay. That uniformly charged symmetric body, we can work out the field at a point. There will be a field around a charged body. We can work out the field at a point using the Gauss theorem for a body which is symmetric in nature and which is charged uniformly. Okay. First one is very important derivation. Out of three derivations, one derivation is removed this year. Only two are remaining. Out of two, you can expect one derivation or problem. Okay. So field due to an infinitely long, actually infinitely long. The length is extends up to infinity. In the figure it is taken only some length is taken, but actually it extends up to infinity. Okay. Infinitely long, straight. Write down the notes actually. So briefly and covering all the points, notes is given here. And write down the notes and read the notes. Later on I will take the explanation. So that I am reading the notes that help you in writing the notes. Okay. Field due to an infinitely long, straight, uniformly charged wire using the Gauss's law. Okay. So here is the diagram. Here is the uniformly charged, positively charged wire is taken. It may be positively charged or negatively charged. But I can't take both at a time. So positively charged wire is taken. So it extends up to infinity. But in the diagram it is not possible to show. So the charge density, one day I have given the definition of linear charge density, then volume charge density, surface charge density, is it not? The linear charge density is positive because what is the linear charge density? Lambda is equal to charge per unit length, Q by L. Q is positive, L is positive, therefore linear charge density. Linear charge density is nothing but charge per unit length, Q upon L. Okay, so it's a sign it is coulombs per meter. Okay, and Q is positive here, charge is taken as positive, L is a positive number, length is a positive number, therefore Q by L is positive, positive upon positive. Okay, so uniformly charged wire is taken, positively charged. Okay, in the diagram a point P is taken, which is at a distance R from the wire, and at the point P here the resultant field E bar is radially outwards, and here are the two line elements, small pieces of the line is taken, P1 and P2, where this P1 and P2 is symmetric with respect to P, means at an equal distance. Okay, symmetric means at an equal distance from the point P. The E1 bar is the field due to the element P1 and E2 bar is the field due to the element P2. Actually, the two fields superposes here, combines here to generate a resultant field E bar. The vertical component, so already it is explained. So look here, the vertical, so it is E1 bar or it is E2 bar. It is in what it is, electric field due to a dipole on the equatorial plane. Same explanation was taken. Okay, so this is the vertical field component of what it is, E2 bar, E2 cos theta. Okay, so this is the vertical component of E1 bar, E1 cos theta. So it's not cos theta, sin theta. Okay, vertically sin, no? So both are equal and opposite. Phi equal, length of the line segment are same, as well as distances are same. Therefore, field at those points E1 bar and E2 bar are equal in magnitude. Therefore, E1 cos theta and E2 cos theta, charge is same, distance is same, then at a point the fields are also same. Okay, therefore E1 sin theta and E2 sin theta are equal and opposite, cancels each other. It is E1 bar is resolved vertically and horizontally. E2 bar is resolved vertically and horizontally. Okay, now therefore E1 sin theta and E2 sin theta are equal in magnitude, opposite in direction, cancels each other. Now the horizontal component of E2 is E2 cos theta and E1 is E1 cos theta. So both are acting in the same direction, adds up to give the resultant field E bar. This point you have to remember. Therefore, the field at a point P is radially outwards, the resultant field. Now either P1 bar and P2 bar alone produces the field at A. No, every line segment produces what it is field at the point P. Look here. So this is our line segment. Produces the field. So like this. This is the symmetric line segment. Produces the field at this point. Vertical of each cancels each. Vertical components of both cancels each other and horizontal adds up. So this is another line segment. Two symmetric line segment to take. This is the vertical component. This is the field at those points. Field at a point is radially outwards due to a point charge. You know that. Radially around the radial direction. Radial direction is the line join of the charge and the point. Okay. So horizontal components again same thing. Vertical components what it is cancels and horizontal component adds up to give the field in the same direction. This is another pair of what is symmetric line segments. Its fields are like this. Okay. Same thing. The vertical adds up the fields at the point P due to these symmetric line elements or at the point P is like this in this direction. So radially it comes along radially along the line join of the point and the charge. Here is the charge, here is the charge. These two are the symmetric. Just look at the explanation carefully. These are the two line segments. So which are symmetric with the point P and its field at the point P is along the line join of the charge and the point. And these are the two fields E1 bar and E2 bar due to P1 and P2. Vertical cancels each other, horizontal adds up and gives the resultant field in the same direction like that. Every pair of symmetric line segment produces the field at the point P. Their vertical components cancels and horizontal component adds up to give the resultant field E bar at the point P. And it is all horizontal components of all the line elements will be in the same direction. Therefore, all the line elements, horizontal components adds up to give the resultant field E bar, which is along the direction of radially. Radial means the line join of the wire and the point. Okay. So now, therefore, field at the point P is radially outwards resultant field. If the charge is positive, if the charge is negative here, it is negatively charged, the field is radially inwards. Okay, the field will be like this, radially inwards at this point. Okay, the charge is negative, you know that charge is negative, field is towards the charge, and charge is positive, the field is radially outwards. Okay, away from the charge. So radially, if the charge is negative, the charge body is negatively charged, the field is towards the charge. Radially towards the charge, if charge is negative, positive, the field is radially outwards. Radially means along the line join of the charge and the point. So, now consider a cylindrical Gaussian surface. Imagine it is. So, I have drawn dotted cylinder now. Cylindrical Gaussian surface. It is imaginary one, not a wire is not actually covered with this cylinder. Imaginary cylinder you consider. With height here, okay, height means length of the cylinder is L, and the radius of the cylinder is R. The point P is also at a distance R from the wire, and the axis of the cylinder will have an axis now. The cylinder will have an axis is coinciding with the wire. Therefore, automatically the point P comes on the curved surface of the cylinder. What is the curved surface? So here is the cylinder. This surface is called cylindrical shape set, and chalk is the cylindrical body. This is surface in there, no? The round surface. This surface. My finger is a cylinder actually. this skin is the what it is, the curved surface, or the skin itself is the what, the curved surface. Actually the point P comes on the curved surface of the cylinder. Curved surface area is how much? 2 pi RL. Okay, what is the curved surface area of a cylinder? 2 pi R into L. 2 pi RL. S is equals to 2 pi RL. Now let us work out the flux through this cylindrical surface by two techniques. One is by the definition of flux. What is the definition of flux? Says that pi is equals to E bar dot delta S bar. E bar dot S bar. For a uniformly charged body, no question of considering delta pi. That day when they have explained, if uniformly charged body is there, then field at the points will be uniform. In that case, the field can be worked out, flux can be worked out by pi is equals to E bar dot S bar, not delta S bar, not necessary. Okay, full surface area can be considered at once. And E bar dot S bar, that's equals to ES cos theta. That is the one way to calculate the flux through a surface. And second one is by the Gaussian theorem. It is a closed surface. No, the charge is inside it. Q is the charge inside the what it is, the Gaussian surface. Now, when Q is the charge inside the Gaussian surface, then what is the flux pi? Pi is equals to Q upon epsilon. What is the Q actually? Q is equals to lambda L. Therefore, flux pi is equals to, I have written somewhere here, pi is equals to lambda L upon epsilon. So, flux is worked out by two methods. One is by the definition of flux. Flux pi is equals to E bar dot S bar, that's equals to ES cos theta, because E bar dot B bar is AB cos theta. And another method is Gauss's theorem, Gauss's law. Flux pi is equals to a closed surface which contains a charge Q inside it is equals to, which encloses the charge Q. Pi is equals to Q upon total charge enclosed by the Gaussian surface divided by epsilon naught, absolute permittivity. What is the Q here? Q is lambda L. Therefore, flux pi is equals to lambda L upon epsilon naught. That's all. No mathematical part, only explanation. Then both the fluxes are equal. By equating both the fluxes, it is also pi, it is also pi. Flux through this cylindrical surface. This is also flux through this cylindrical surface area. Therefore, flux pi can be equated. Therefore, ES cos theta is equals to ES cos theta. Here it is ES cos theta. It is 2 pi r. Theta I have taken it as 0. Later on, we will explain why it is 0. 2 pi r into E. Then by equating these two, you will get E, an expression for the field E. That the intention of this derivation, to get a field at a point due to a uniformly charged wire which is straight in nature, and what is the length of that wire? Infinity. Okay, so up to infinity not extend. Now coming to the important explanation. Here it is flux. While calculating the flux through the surface, by the definition it is ES cos theta, no? E bar dot S bar, that's equals to ES cos theta. Actually, so there are curved surface as well as top and bottom surface. This is the top surface, this is the bottom surface, and this is the curved surface. This is the top surface of the cylinder, bottom surface of the cylinder. This is what curved surface. Okay. Now, actually flux, there is no flux is passing to the top and the bottom. Only flux is passing to the curved surface. Why it is? That particular point is important. Just I will explain and try to remember. Okay. So now look at the field. Field is in this radially. Look at the this is the curved surface. This is the curved surface of the cylinder. Field is radially outwards. Now look here. The surface is perpendicular to what? The field direction. In this case, theta is 0. Why theta is 0? Theta is not 90. Because theta is the angle between the normal. This is the surface. Okay. This is the cylindrical surface. Okay. This is the cylindrical surface. Cylindrical in shape. Wait a minute. Okay. This is the cylindrical surface. Now field, if you look at the diagram, field is in this direction. Now actually the normal to the surface is also like this, normal to the surface. Okay, I am just considering this is the direction of the field. This is the normal to the surface. Normal is perpendicular. What is the angle between the normal and the direction of E? That is taken as theta in the definition of flux. Theta is nothing but the angle between the normal. Normal is perpendicular drawn to the surface, and the field E is 0. No? Therefore theta is 0. What about this top? This is the top and the bottom. Field is in this direction. Normal to this top and the bottom surface. Normal to this top and the bottom surface is like this. This is the top surface. This is a normal draw. This is the top surface. This is the field direction. Okay, and this is the top surface. What is the angle between them? 90 degree. Means theta is 90. Actually, theta in the definition of flux pi is equal to Es cos theta. Theta is the angle between the normal and the direction of the field. 90. Therefore, cos 90 is how much? 0. Therefore, no flux is passing through this top and the bottom surface. Only flux is passing through curved surface area. But it is 2 pi RL. Therefore, the flux pi is equal to Es into cos theta. That's equal to E. S is 2 pi RL curved surface area into cos 0. For the curved surface, theta is 0. For the top and the bottom surface, theta is 90. So, therefore, when theta is 90, no flux is passing. Okay. So, in the definition of flux pi is equal to Es cos theta, if theta is 90, then no flux is passing through that particular area element. Okay. If theta is 0, then the flux is maximum. That's equal to E into S cos 0. That's equal to E into S. S is 2 pi RL cos 0. Therefore, 2 pi RL into E. Okay. Now, equating both the fields, you will get the quantities. So, I will explain the notes once again. So, I am reading the notes. Explanation is over. Look here. At the quantities, top and the bottom. This is the direction of the field E bar now. And this is the normal to this top surface now. So, what about normal? Perpendicular. The angle theta is what? 90. Theta is equal to 90. Therefore, the flux pi through this top and the bottom surface. Here also field is like this. So, field is always radially outward. This straight conductor. Field is always radially outward. Explanation is taken. So, at this point, so it is theta is what? Normal to this top surface. Normal is perpendicular. This surface is perpendicular to ground 90 agಬೇಕು. Surface ಮತ್ತು ಇದರ ಮಧ್ಯೆ 90 ಬರಬೇಕು ಲೈನಿನ ಮಧ್ಯೆ. ಅದು perpendicular normal ಅಂತ ಕರೀತೀವಿ. Therefore, so theta is 90 means what is the flux pi? Es cos theta. Cos 90 is 0. No flux is passing through. In the explanation of what? Definition of flux pi. Both the diagrams were given. When theta is 90 and theta is 0. Then how much is the flux? Explanation ಕೊಟ್ಟಿದ್ದೇನೆ ಅದಕ್ಕೆ. Derivation ಬೇಕಾಗುತ್ತೆ ಅಂತ ಅದು ಎಕ್ಸಾಮ್ ಗೆ ಕೇಳೋದಿಲ್ಲ ಆ ಎಕ್ಸ್ಪ್ಲನೇಷನ್. ಬಟ್ ಈ ಡೆರಿವೇಷನ್ ಬೇಕಾಗುತ್ತೆ ಅಂತ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡಿದ್ರು ಫಿಗರ್ ಹಾಕಿ. ಸೊ ಥೀಟಾ 90 ಥೀಟಾ 0 ಮ್ಯಾಕ್ಸಿಮಮ್ ಫ್ಲಕ್ಸ್ ಆಗುತ್ತೆ, ಮಿನಿಮಮ್ ಫ್ಲಕ್ಸ್ ಆಗುತ್ತೆ ಅಂತ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡಿದ್ದೇನೆ. ಟ್ಯೂಬ್ನಲ್ಲಿ ವಾಟರ್ ಹರಿಯೋದ ಎಕ್ಸಾಂಪಲ್ ಅನ್ನು ತಗೊಂಡಿದ್ದೆ. therefore so at the for the top and the bottom surface, theta will be E bar is in this direction, radially outwards, and normally like this, theta is 90. Therefore, no flux is passing. Theta is 90. Therefore, no flux is passing through this top and the bottom. Flux is passing through only this curved surface area. Here, the field is E bar is like this. You get the direction of E bar. And normal is also like this. This is the normal perpendicular to the surface. Normal is perpendicular to the surface. So, normal. Okay. And theta is 0. Therefore, what is the flux through it? Es cos theta. Cos 0. Cos 0 is 1. Therefore, it is. So, S is 2 pi RL. Maximum flux is passing through the curved surface. Therefore, total flux is passing through only curved surface, not the top and the bottom. Understood? Now, equating both the fluxes, we get an expression for E bar. Okay. I will read out the notes. So, diagram is understood. E bar is always radially outwards. It is E bar. Okay. At every point on the cylindrical surface, the field is radially outwards. Okay. So, P1 and P2 are small line elements. E1 bar is the field due to P1 and E2 bar is the field due to P2 at the point P, where P is at a distance r from the wire. Consider an infinitely long straight uniformly charged. I am just reading the notes. Consider all explanations are taken. Consider an infinitely long, straight, uniformly charged wire. Lambda is equal to full stop Q by L to the linear charge density, charge per unit length of the charged wire. Charged wire. Okay. P is a point at a distance r from the wire. P is a point at a distance r from the wire. Consider two line segments P1 and P2. In the textbook, two separate diagrams are given. So I have taken only one diagram, enough. Symmetric with respect to point P means at the same distance. Symmetric with respect to P means, so P1 and P2 are at equal distances from the point P. Okay. E1 bar and E2 bar are the fields. E1 bar, what is the direction of the field? It is along the line join of the charge and the point. No? So in the beginning of the electric field, it is taken, it is radially outwards or radially inwards. Radially means along the line join of the charged element, the point. It is the field is along the line join of the charge and the point. E1 bar and E2 bar of the field due to the line elements. P1 elements means small portion of the line. P1 and P2 respectively. Okay, E1 bar and E2 bar are the fields at point P. So point P due to P1 and P2 respectively are the fields at the point P due to even says due to the elements due to the elements P1 and P2 respectively. Okay. Vertical components already I have explained. This is E1 bar, this is E2 bar, and this is E1 bar. Okay. So the vertical components is like this. It is E1 cos sin theta and E2 sin theta are equal in magnitude, opposite in direction, because resolution of a vector already is explained first year. Here is the vector, how to resolve it vertically and horizontally. And here is the vector like this. The vertically is like this, horizontally is like this. ಯಾಕೆಂದ್ರೆ ಯಾವ ವೆಕ್ಟರ್ನ ರಿಸಾಲ್ವ್ ಮಾಡ್ತೀವೋ ಅದು ಮಿಡ್ಲಿಗೆ ಬರುತ್ತೆ. ನೀವು ವರ್ಟಿಕಲ್ ಅನ್ನು ಹೀಗೆ ತಗೊಳ್ಳಿಕ್ಕೆ ಬರೋದಿಲ್ಲ, ಇದು ಹೊರಿಜಾಂಟಲ್ ತಗೊಳ್ಳಿಕ್ಕೆ ಬರೋದಿಲ್ಲ. This is resolved. Therefore, one component is in the left, one component is in the right. The vertical ಹೀಗೆ ಬಂತು, horizontal ಹೀಗೆ ಬಂತು. ಸರಿನಾ? Vertical ನೆಗೆಟಿವ್ y axis ನಲ್ಲಿ ಬಂತು. ಇದು ಯಾವ ವೆಕ್ಟರ್ನ ರಿಸಾಲ್ವ್ ಮಾಡ್ತೀವೋ ಹೊಡಿತೀವೋ ಅದು ಮಿಡ್ಲಿಗೆ ಬರುತ್ತೆ. ಅದು horizontal is and vertical should be the left and right side. So ಇದು vertical component ಹೀಗೆ ಕೊಂಡು ಡ್ರಾ ಮಾಡ್ತೀವಿ. ಅದು vertical component ಬರಬೇಕು. It is E1 bar. ಅದು vertical component ಹೀಗೆ ಬರುತ್ತೆ, horizontal ಹೀಗೆ ಬರುತ್ತೆ. ಇದು E2 bar actually. ಇದನ್ನ ಹೊಡೆದಿದ್ವಿ, component means ಇದನ್ನು ಎರಡು ಭಾಗ ಮಾಡಿದ್ವಿ. horizontal ಹೀಗೆ ಬರುತ್ತೆ, vertical ಹೀಗೆ ಬರುತ್ತೆ. ಸರಿನಾ? So ಒಂದು ವೆಕ್ಟರ್ನ ಹೊಡಿಬಹುದು along the x-axis and along y-axis. So ವೆಕ್ಟರ್ ಹೀಗಿದ್ರೆ y-axis component ಹೀಗೆ ಬರುತ್ತೆ, x-axis component ಹೀಗೆ ಬರುತ್ತೆ. So it is the case of E2 bar. E2 bar ಹೀಗಿದೆ, ಹಾಗೆ vertical ಹೀಗೆ ಬಂತು, horizontal ಹೀಗೆ ಬಂತು. E1 bar ಹೇಗಿದೆ ನೋಡಲಿ ಹೀಗಿದೆ, ಅದು vertical ಹೀಗಾಯ್ತು, horizontal ಹೀಗೆ ಬಂತು. E1 bar ಅಲ್ಲ. So horizontal and vertical. Horizontal means along x-axis, vertical means along y-axis. So vertical ಮತ್ತು horizontal ಮಧ್ಯದಲ್ಲಿ the vector is to be resolved ಬಂದ್ಬಿಡುತ್ತೆ, ಆಯ್ತಾ? So therefore cancels each other. So and horizontal components acts in the same direction, ಎರಡು along x-axis ಆಗುತ್ತೆ, adds up to give the resultant field E bar, which is radially outwards. Therefore resultant field E bar ಎಲ್ಲ ಪಾಯಿಂಟ್ resultant field ಬರುತ್ತೆ, because not only single point charge is there, uniformly charged continuous charge distribution is there, because every line element produces the field here. ಎಲ್ಲದು vertical component cancel ಆಗಿಬಿಡುತ್ತೆ, horizontal ಎಲ್ಲ ಒಂದೇ ಸೇಮ್ ಡೈರೆಕ್ಷನ್ ಅಲ್ಲಿ ಬರುತ್ತೆ, ಆಡ್ ಆಗಿಬಿಟ್ಟು resultant field E bar ಅನ್ನು ಕೊಡುತ್ತೆ. Radially outwards or inwards, accordingly lambda is greater than 0 or lambda is less than 0. Lambda positive ಇದ್ರೆ E bar is radially outwards, lambda is negative, E bar is radially inwards. ಹೊರಗಡೆ ಬರುತ್ತೆ, ಆಯ್ತಾ? E bar is equivalent towards the charge, because charge is negative, field is towards the charge is positive, field is away from the charge radially. Okay. Consider a cylindrical Gaussian surface of height L. Consider a cylindrical Gaussian surface of height L and radius R with axis coincides with the wire Therefore, the point P lies on the curved surface of the cylinder. According to the Gauss's theorem, flux through the cylindrical surface pi is equal to q upon epsilon. What is the q? Q is equal to lambda into L, lambda L upon epsilon, because lambda is equal to q by one section is over. No flux is passing to the top and the bottom surface of the cylinder. No top and the bottom surface of the cylinder because theta is 90. Only flux is passing through the curved surface. Passing through the curved surface area. S is equal to, what is the curved surface area? This is the curved surface area. S is equal to 2 pi r. Okay. Therefore, pi is equal to Es cos theta. Theta is how much? 90. S is how much? 2 pi r. Sorry, theta is 0. For the curved surface. For the curved surface, theta is 0. This is the curved surface. The field direction is like this. And normal to the surface is also like this. And theta is the angle between the normal and the E bar. Therefore, both are parallel, means theta is 0. The top and bottom surface, the normal is like this, field is like this. This is top surface, this is the bottom surface. Theta is 90. Angle between this normal and the field direction is 90. Therefore, no flux because Es cos 90. Cos 90 is 0. No flux is passing through. Field lines are passing through this top and bottom. Only field lines are crossing this curved surface. So, E 2 pi RL into E, because cos 0 is 1 now, therefore E is taken to the end, 2 pi RL into E, both are pi, equating pi, that's all. That's the end of the derivation. These diagrams given in the left and right are not necessary. From 1 and 2, both are pi now. Let us take 2 first. E 2 pi RL, because I want E, no expression for E. 2 pi RL into E is equals to what? Lambda L upon epsilon. L kattagate. It is lambda L cancels. Okay, therefore E is equals to lambda upon 2 pi R into epsilon. So that is the expression for the field. Magnitude will be put in. Okay, so therefore E bar is equals to E bar. Field is a vector quantity, no? E bar is equals to 2 pi. Unit vector direction bar direction. When bar is taken, you have to put the direction. What is the direction? Direction of any vector is along the unit vector. Therefore, lambda upon 2 pi r epsilon naught into n cap. Field is radially outwards, means perpendicular to the surface. Field is direction is perpendicular to the curved surface. Therefore, n cap is the unit vector. N cap is the unit vector. N cap is the magnitude of the field line, the direction. N cap is radially outwards if charge is positive. N cap is radially inwards. Again, the field direction is the direction. If charge is negative, the N cap is radially outwards, then the field is radially outwards. And if a charge is negative, the wire is negatively charged, then the field is radially inwards, then N cap is also radially inwards. Therefore, N cap is a unit vector radially outwards or inwards, and it is perpendicular to the plane of the curved surface. N cap is perpendicular to the curved surface. Here, perpendicular where N cap is the unit vector. What would N cap is one explanation. N cap is radially unit vector. Radial unit vector. Short again, radial unit vector. Where N cap is a radial unit vector. Radial unit vector. Radial unit vector. This is the end of the derivation. Okay, unit vector means radial means it is the line join of the point and the charge. Radial means it is the line join of the point and the charge. Here is the line, here is the point. This is the radial. Radial unit vector in the plane normal to the wire. In the plane normal to the wire. In the plane normal to the wire. Number 8. Normal to the wire. Normal to the wire. Okay. In the plane. ಯಾವ plane will ಬರುತ್ತೆ? Plane normal to the wire. ಇದು wire. Suppose this is the wire. ಆ wire ಗೆ normal ಇದು normal ಆಯ್ತಾ? This is the normal.